This is lesson 4 of the chapter 5 on radians, and this is about solving trig equations when we're working in radians. You already know how to solve trig equations when working in degrees. We did that in year 1, and this is just an extension of that. Sometimes we will need to solve equations in degrees, and sometimes we will need to solve them in radians. And you'll know from the question if we're working in degrees or in radians, because you'll see from the information we're given if the range of values that we're solving for is in degrees or in terms of pi, and therefore in radians. So, a couple of things that are useful to remember is that when we solve trig equations, we don't just look for one value, we look for all values of x within a range. So if I was solving between, this is minus 2 pi to 2 pi, if I was solving within that range, there would be 4 answers at whatever this value is. Say it's a half, just for argument's sake, but then we would need to give 4 answers. The calculator gives us this one, we would need to work out the other 3, which we know how to do in degrees because we know this value is 180, and therefore in radians that value would be pi. This value would be minus pi, minus 2 pi, and 2 pi. And that's true for the cos graph and for the tan graph as well. So again, pi would be here, 2 pi, minus pi, and minus 2 pi. And the tan graph repeats every 180 degrees, so that's every pi radians. So pi there, pi over 2 is an asymptote, 3 pi over 2 is an asymptote, 2 pi would be there, and the same for the negative side as well. So let's have a look at some important properties that we need. We looked at this in 5b, but these are the ones I think are most important for when we're working out missing angles or solving equations given a range of values for x. The first one is to remember that sine of negative x, so if I've got a negative x here, so here's my minus x, what would that be in terms of sine x? What would sine x equal? Well, it would be equal to the negative of sine x. Those two things are always equal. So negative of sine x is equal to sine of negative x. That's actually always a property of functions that we describe as being odd, and you know you've got an odd function if there's rotational symmetry around the origin, and this feature is always true if you have an odd function. For cos of minus x, if this is cos of, if minus x is here, then that's just equal to cos of x. So there's no minus sign, it's just equal to normal cos x. Sine of pi minus x is just how we would get the next value. So that's equal to sine of x. And cos of 2 pi minus x is how we would get the next value for cos. And that's equal to cos x. So those are the top 4, I think, things to remember when working out other values of x's when solving trig equations. The tan one I've not bothered to write down, but tan of x, to get the next value for tan x, that's equal to tan of just pi plus x. And remember, if we wanted to go further and get extra values of these again, we would do sine of 2 pi plus x and cos of 2 pi plus x to get the third values, and then we would do 2 pi plus this value and 2 pi plus this value to get the fourth values. Whereas for tan, we just keep on adding lots of pi. So pi plus x, 2 pi plus x, 3 pi plus x, and so on. So let's go through some examples of questions we might be asked. I've gone for a variety of different things that we might be asked to cover, it's all the same stuff as we had to do in degrees. I can't remember what the chapter number was in the trig chapter in degrees, but it's anything you had to do in degrees, you now might have to do in radians. So it's kind of repeating all those same skills, which is a really good recap to do, but now adding in the fact that we're working in radians instead of degrees. First thing to notice is that this is how we know whether we're working our answers out in degrees or radians. Because that's in terms of pi, that means we're in radians. If it had said 360 degrees, then we'd need to make sure our calculator's in degrees. So solve this equation, which means find the values of theta, giving all roots in the interval 0 to 2 pi. So first thing I'm going to do is what we would have always done, is work out the inverse cos, making sure your calculator's in radians, inverse cos of minus 0.7. And the answer to that is 2.346. We need all the equations from 0 to 2 pi. So I'm going to draw myself a quick cos graph from 0 to 2 pi. Which looks something like that. And our minus 0.7 is like here somewhere. So this is 2.346. And we need all the values. In other words, we need this extra value. We need to find out what this number is. And we keep going back to the gaps. It's all about the gaps. This gap here is 2.346. So this gap here will be 2.346 as well. So our second value that we're looking for will come from 2 pi minus 2.346. That's what we wrote here as this one here. 2 pi minus our angle. So I'm just going to do 2 pi minus ants on the calculator to get my second answer. And this one only has 2 answers in the range that we are given, and that's 3.94 radians. You wouldn't lose marks if you didn't lose radians, if you didn't write down radians, but it's nice to show that you know what you're talking about. Okay, different type of question. What I've not said so far is that the equations that we know that are true, like that sine squared plus cos squared equals 1, and that sine theta divided by cos theta is equal to tan theta, that's still true in radians. So sine theta still equals, sine theta over cos theta still equals tan theta, and sine squared theta plus cos squared theta is still the same as 1, whether we're working in degrees or in radians. So we will be expected to use these equations, these relationships, when solving trig equations as well. Here we've been given that tan theta is equal to cos theta, and we're asked to find the values of theta that make that true. That's making me think of this equation. So I'm going to turn tan theta into sine theta over cos theta. And I'm then going to times both sides by cos theta, so that I've not got any fractions. And that gives me cos squared theta. We can really only solve trig equations if we've only got sines or coses or tans, which we don't have here yet. But what we can do is we can say that cos squared theta is equal to 1 minus sine squared theta. So that sine theta is equal to cos squared theta, but that's equal to 1 minus sine squared theta. And now I've just got sines. And if I add everything to the left hand side, still got my sine theta there, I'm going to have sine squared theta, which I've moved, plus my sine theta in the middle minus this one now is equal to 0. And I've written that in that order so that it looks like a quadratic, because we can now solve, if I let x equal sine theta, we can now solve x squared plus x take 1 equals 0. Now that's a quadratic, but it doesn't solve nicely, so we're either going to need to use the formula, use completing the square, or use our equations button on our calculators. And I'm going to use the calculator. They're not going to expect you to do loads of working out when this is within a question. So I'm going into option A on my class whiz. It's a polynomial, the degree is 2, so we've got 1x squared, 1x, take away 1, and that gives me a value of x that's minus 1 plus or minus root 5 over 2. So we've got values for x. That means that sine x is equal to those two values. There's two values there. There's the minus 1 plus root 5 over 2, but there's the minus sine x, minus 1 minus root 5 over 2 as well. So I'm actually going to look at this one first, just for speed, and you'll see why in a second. If we draw out the sine graph, and try and do the inverse sine of this value, inverse sine of minus 1 minus root 5 over 2, then we get an error. The reason we get an error is because this number here is actually smaller than 1. So we've got our calculators trying to work out a sine value that's actually below that minimum point. It's down here somewhere. So this won't actually produce any answers. We can get rid of this altogether and say no solutions, because the sine graph has to have answers that are between minus 1 and 1. This one does give us answers. This number is between minus 1 and 1. This number is actually 0.618. So that one's fine. So if we go over to this side now, I'm going to draw another sine graph. In fact, I need to pay attention to what the interval was. It was minus pi to pi. So let's draw between minus pi and pi, which would look like that. And our calculator has given us a value of 0.618 as a height. So that's, let's say that's there. So when we do the inverse sine of that, we're going to get this value. So inverse sine of that answer is 0.666. So that's here. To get the other value, we want to do pi minus, sorry, I should have written theta there, not x. Theta will also equal pi minus 0.666. This gap's 0.666, so pi minus that. And that is 2.475. So those are our two answers, 0.666 and 2.475. You can always check if your answer's right. I've just moved the cos theta over to the left hand side here. So I can do tan ants, and that will have the 2.475 number stored in it. Tan ants minus cos ants should give me 0, which it does. I could go back to the 0.66666 and do the same thing, which also gives me 0. So I can be really confident that those are correct answers. And move on to the next question. So I've got another question here, which is another equation. You can kind of tell straight away that it's one of those hidden quadratics, stealth quadratics we sometimes call them, because we've got sines squared and we've got coses that aren't squared. Again, we're going to need to turn everything into either sine, cos or tan. Doesn't matter if there's some are squared and some aren't. And because the cos here can't really be turned into a sine, we're going to want to turn the sine squared into a cos squared. So we're going to use the fact that cos squared is 1 minus cos squared is equal to sine squared x. So I can replace this sine squared x with 1 minus cos squared. I've noticed also that there's an interval of 0 to 2 pi. That's what tells me that we're working in radians if we're in an exam. And I'm going to rearrange this to make it look like a quadratic. So we've got 17 cos x plus 3 minus 3 cos squared x equals 13. I'm going to move everything to the right hand side so that my cos squared x is positive. So 3 cos squared x minus 17x, and I'm going to take away 3 from both sides. That will give me plus 10 is equal to 0. This actually factorises, I think. Oh, I've written x. I should have written cos x there. I can let y equal cos x if you want to, and then rewrite that as 3y squared minus 17y plus 10 and solve that. You don't actually need to though. You can write 3 cos x and cos x in your brackets so that you're not having to switch to y's and then back to cos x's. So you can do this, but you don't actually need to. In order to make 17, I'm going to want a 5 here. This is my best chance of factorising this quadratic. If this doesn't work, I don't think it's going to factorise. It's going to be 2 minuses, because that's going to give me 15, and then take away 2 more will give me minus 17. Which means that cos x is equal to 2/3, or cos x is equal to 5. Similar to the previous example, we can get rid of this. This isn't going to give us valid solutions because cos x has to be between -1 and 1, and that's bigger than 1, so that's not going to work. This is the only thing that's going to give us solutions. So the next thing I'm going to do is draw a quick cos x graph between 0 and 2 pi. And I'm going to mark on roughly where I think my 2/3 height is. And mark on all of those heights so I know how many angles I am looking for, and I'm looking for 2. The calculator is going to give me this value. So inverse cos of 2/3, making sure that your calculator is in radians, gives me 0.841. And then how do we get the other answer? Well, we're going to do 2 pi minus that x value. Which is 5.44 to 3 significant figures because they've not specified how they want my answers. So 0.841 radians to 3 significant figures and 5.44 radians to 3 significant figures. Again, you can check if that's right. You can type those numbers in at the top, type in the left hand side and see if you do get 13. If you don't, you've made a mistake. If you do, then you know you're right. The last example is where we've got some other multiple of x in here, which we sometimes struggled with in year 1, but we need to make sure we're really, really good at these in year 2. We can't afford to lose marks on this type of question. So we're rather than trying to work with a sine 2x graph, which you can do, you can work with a sine 2x graph and think about the transformations. I've always found it much easier than, rather than do that, is to just extend the range and find all the values of 2x between 0 and 4 pi and then just halve all the answers. It feels much more straightforward. The only thing with that is you've got to remember to do the halving right at the end. So let's get started. The first thing I'm going to do is find the inverse sine of minus 0.4, which is minus 0.412, and that's a value of 2x, minus 0.412. And I'm going to store that number into the calculator memory. That's going in memory A, because I feel like I'm going to need to use that number over and over. That's not actually going to be a very useful answer because that's not in the range, in the 0 to 4 pi range. So I'm going to have to discount that number, but I am going to need to use it to get the numbers that I want. So next thing I'm going to do is think about the sine graph. But I'm going to draw it for 0 to 4 pi. It's a bit wobbly, but it'll do. And I'm going to need to go back a little bit so that we can see our negative answer that the calculator's given us. So the calculator's given us this angle here. This is our minus 0.412. We want these 4 answers. But remember, these are all values of 2x. We're going to need to halve them all later on. So this gap here is 0.412. I want this number here. Remember, this is pi, 2 pi, 3 pi and 4 pi. They're not going to be hard to find. We want these two. These are the main 2 ones that we need to get first. So in order to find this value, I need to do pi plus the 0.412. So my first useful answer for 2x is going to be pi plus 0.412. Now you can times this a by minus 1 if you want to turn it positive and then add it, or you can do pi minus answer a, or pi minus answer if it's still the answer on your calculator display. But you're looking for 3.55. Remember, we're adding a bit on. We're expecting this number to be bigger than pi. So there's 3.55. How do we get the next one? Well, and actually I'm going to save that to memory B so that I can halve them all correctly later. The next one we're after here will be 2 pi minus the gap. 2 pi minus 0.412. So in order to do that, if you've turned your 0.412 positive, you can literally do 2 pi minus that 0.412. I'm going to need to do 2 pi plus a, so that this answer is a bit less than 2 pi, which is 6.28, so I'm expecting a number less than 6.28. Sorry, I need to do 2 pi plus a, which is 5.87. That's going to go in memory C. So I've got in memory B 3.55 and in memory C I've got 5.87. To get the next two, what we're going to do is use the fact that the gap between this number and this number is exactly 2 pi because it repeats every 2 pi. So from here, from this point all the way down, up and down again, I've travelled along that line, I've travelled 2 pi radians. So to get my third value, I'm going to do 3.55 or memory B add 2 pi. Which is 9.84. That's going in memory D. And then I need to do a similar thing to get the last value with my 5.87. That will be 5.87 plus 2 pi. So C plus 2 pi is 12.15. That's gone in D. This is going in E. So there are my 4 answers now for 2x. 1, 2, 3, 4. The last job now that we've got all the 2x values, is to halve all of these numbers. So I'm going to do B divided by 2, C divided by 2, D divided by 2, and E divided by 2 to get my actual values for x. And because I've used the calculator memory, all of these answers are going to be accurate to 3 significant figures when I round them. So 1.78, C divided by 2 is 2.94, D divided by 2 is 4.92, and E divided by 2 is 6.08. And again, you could check if all of these numbers give you minus 0.4, but notice that they have all now dropped below 2 pi. They've gone less than 6.28, 2 pi. And that's fitting with the range of values that we were asked to provide answers to. So you should now be able to have a go at exercise 5E, which starts on page 131 in the Edexcel textbook. As always, any questions, drop me a comment or send me an email or a message on Show My Homework. We're almost done with the Radians chapter now. We've got a little bit left to do on small angle approximations, but that is the last part of this chapter.